Okay, am I audible, ma'am?
Yes, ma'am.
Yes. Okay, good afternoon. So, in today's class, we are going to discuss about a topic which will be relevant after the code generation phase. Okay, so like we have studied that there are different phases of compiler, and we have broadly classified that as analysis phase and synthesis phase, right? So, in the analysis part, we have talked about the lexical analysis phase, syntax analysis, and semantic analysis phase, right? And in between, we have intermediate code generation after that, right? So that we will study later in the physical class. So, and even in your teaching plan, this part comes after your SDT, okay? So we'll discuss first about this. So this is basically in your compiler you're going to generate a code, right? So it is a code which is either a assembly language code or whatever code that you want to, the target program you're going to generate. It can be, it is not necessarily the assembly language, but you can also go for a machine language. So now the target program, it has to run, that has to be executed finally. Okay, so that target program, the compiler, it is going to create an environment where this target program is going to be run, and it manages that environment. Basically, when we what is the process of compiler? We are converting a high level language into the machine level language. Okay, so the source program, you have several things attached with your program. Okay, you are using several So there are several abstractions involved in your source program. So it may be having the names, the scopes, the we talk about the global variable and local variable, right? When you are doing a program, you might come across those terms. The some of the variables may be local to a particular function, and some of the variables may be global. Okay, so the scope of the things and data types, operators, procedures. So all these are all available in your source program. So as you are converting your source code into a high level language source code into machine level code, the target program, it has to be um, run properly with the cooperation of the operating system and your the target system. Okay, all these has to cooperate, and so we need a runtime environment. So this is what is created by the compiler, and it creates and also it manages this runtime environment where the target program is going to be executed. Now, what are all the issues this runtime environment will face is that the basically on the location storage locations. So how to allocate space for the all the named objects, okay, all the named program objects, whatever it is, either it may be your operators or the variables or whatever objects that you are going to use in your program, how the storage can be allocated for that, and the mechanism for the target program to access the variables. So it needs to access the variables for doing the execution. On its execution part, it has to access the variables and the data, and it has to compute the things. So how that has to be done, and the linkage between the procedures. So you may have several procedures in your code, and some of the procedures may be independent, and some of the procedures they call some other procedure, and so on. So how it is going to be linked with each other. And then the mechanism for passing the parameters. Okay, so you would have studied about your actual parameters and the formal parameters and so on. Okay, so how these parameters can be passed into your functions or the procedures, and how interface can be made between the OS or between other IO devices and your program. Okay, so all these things are going to be managed by the compiler in this runtime environment. So when you consider any program, the each of this functions or the procedures that you're going to use, or the entire program structure that you have, it is going to be stored in an address space where it is having a where we call that as a logical address space. Okay, so it is going to be stored in a location, maybe in a sequential order. You may be having some byte ordering system or whatever it is, so it is going to use some logical address. But then when this target program, when it needs to be communicated with, when all these operating system and your target machine has to cooperate with all these things to get your target program to be executed, it has to be mapped with the physical addresses. I think in operating system you would have studied in detail about your logical address space and physical address space and so on. I hope so, right? So you would have. Okay, so the conversion of from physical address to the logical address to physical address. Okay, this you would have studied in your operating system. Okay, so we need not bother about that now. But basically, how the memory is going to be divided, and what are all the various areas we are going to have in the memory to store your target code. So this is how your the runtime storage organization is going to be have, and the memory is going to be divided into various areas. So the first one we have code. Okay, so what it represents is the you have a target program, right? You have a target program, and you know the size of the target program even at the compile time. So during compilation, you know the size of your target program, and so you can allocate memory for that target program. Okay, so that is static. The size of this target program would be static, and you can assign, or you can give space for assigning your, or placing your target program in the memory. So this is the place where your target program is going to be stored. And then we have some space for static data, like some of the locations for the global constants, or the information that is required to support your garbage collection, and so many other static data. Okay, so this also we would be knowing the size of the data at the compile time itself. So then you can again give space for those data during the compile time itself. Okay, because these are all fixed uh, sizes. And then we have two important areas which is going to be used for the dynamic allocation of memory. Okay, so you'd have studied about stack as well as heap in data structures. So both are both are memory. They are going to allocate memory dynamically. Okay, so for example, you would be using the function malloc in your C programming, right? So it means that it is going to allocate the space dynamically during the runtime. And so for such things, we are going to have heap and stack. So basically, the memory is going to be arranged from the lower order address towards the higher order address. Okay. So this, so for example, let us start from 0, 1, 2, and so on. Okay, it may be the byte addresses. So the lower order addresses will be at the it starts from lower order address and it goes growing towards the higher order address. So we have on both the sides this heap and stack. On opposite sides we are going to have, and the stack will grow towards the higher order address and heap will grow towards the lower order address. So that is how this stack and heap is going to be used. So this area, as you see, it is written as free memory. That means the the allocation made in stack or in heap, it is not going to be a static one. So if you are going to push some of the data into the stack, then obviously you will be popping out when it is not needed. So then automatically your memory size will get reduced in stack. That means the memory space will be released. Okay, so you can use it for some other purpose. So we have stack and heap, which is going to be grown at the during the runtime. And so usually in this stack, we are going to have the we are going to store the data structures, which is called as activation records. So we will see that while we are. Okay, so this is also the similar thing. How we are going to allocate the space for the generated target code and the data object of your source program. So as we have seen in the previous slide, the places of the data objects that can be determined at compile time will be allocated statically. So that is what we have in the previous slide, the code and the static data area. And there are some of the things which is going to be allocated only during the which can be known only during the runtime dynamically. So that we call it as for that we can allocate storage space using this stack or heap, and that is done during the runtime, okay, dynamically. So again, similar to that, the static and dynamic, it means that the compile time and runtime. So a storage location decision is static if it can be made by the compiler looking only at the text of the program, not at what the program does when it executes. So only by looking at the program size, if you're going to allocate space, then that is static allocation. And if you are doing the decision dynamically, okay, because if you are getting the input from the user, and if you do not know the size of the input that you are going to receive, then you cannot allocate during the compilation time. So that can be known during the execution only. So if the decision is dynamic, and if it can be decided only while the program is running, then we call that as dynamic allocation. Okay. So, so as we have seen, we have two such dynamic allocations. One is using stack and another is using heap. and but what we are going to study is about only the stack storage. So now what for this particular that every time when you call a procedure or a function, so normally you would be having you have a function, and each of the function you may be having a you may be having some local variables. Okay, so you'd be using the local variables inside that function. So now, once a particular function is called, what happens is an activation record will be created. Okay. So for whenever you are calling a function or a procedure, it means that you are activating that procedure. Okay. So what happens is an activation record will be created for each function every time. Not it means that for every function it is created, but whenever it is called, okay, whenever a function is called, an activation record will be created. And what we are going to use, how this stack is going to be used is, whenever a function is called, all the local variables that we are using inside that particular function, that is going to be pushed into the stack. Okay, and when this function gets terminated, okay, once this function gets executed and it is over, then the all the variables that you have already pushed into the stack will be popped off, and your stack space will be relieved. Okay, so this is how we are going to use the stack for whenever we are going to execute a function or a procedure. And one more thing, this procedure activations has to be nested in time. What is the meaning of that? So while you are doing, while you are calling a function, inside the function you may be calling another function. Okay, so that means when this function is called, you are creating a activation record, and inside the function again you are calling another function. So that means an activation record corresponding to this function is also created. Okay, and so consider that the outer function is p, and the inner function we call it as q. If procedure p calls procedure q, then even in cases of exemptions and errors, q will always terminate before p. Okay, it has to follow that order. So this is the outer function that was called initially, and from inside this function we are calling another function. So if this function gets terminated, whether it is normally terminating or whether it is getting aborted due to some error or due to some exceptions, whatever it is, this has to terminate first before this function is getting terminated. Okay, so the this all the activation. So now what we have seen, for when this function is called, when this procedure is called, an activation record will be created, and when this function is called, again another activation record will be created. So these are all, this we call it as activation of procedures. First this procedure is activated and then this procedure is activated. So during the runtime, as these procedures are activated, we can represent it using an activation tree. Okay, and each procedure activation has an activation record. So we'll see an example, then we'll come back to this. So here we have a So here we have a program for quick sort. Okay, so it is going to read 9 integers and into an array and sorts them using the recursive quick sort algorithm. I hope every one of you knows what is the quick sort algorithm and how it works, right? So initially, when you give an array of elements, it will call for the partition function, and it divides the array into two based on a pivot element, right? It uses a particular element in the set of elements as a pivot element. Either you can choose randomly or from the beginning or from the middle. Okay, so a pivot element is chosen, and based on that, your array will be splitted into two. So the elements less than the pivot value and elements greater than the pivot value. So that is what you will do. And then again, what will you do? Again, for the elements that are less than the pivot, you will be again calling the quicksort function and apply the same thing. And here similarly, for the elements greater than the pivot, again you will apply the quicksort. So is it visible? Is the slide visible clearly what is written?
Yes, ma'am.
Okay. So if you see here, we have different functions available here. So we have a function read array. It is going to read 9 integers from a of 1 to a of 9. And then we have a partition function. Okay. So when the array of integers is given to this partition function, it is going to pick a separator value, okay, which we call it as pivot or any other name if you use. So we are going to pick a separator value and partition that into two sets, okay. And so we will have the elements less than pivot in one set and elements greater than pivot in another set. And then you can see we have another function which is the main thing, quicksort function. So where you will be passing on, so initially it will pass on the entire set of elements, and from where this partition function is called, and it divides it into two sets. So in the first set we have the values starting from m to I minus 1, and then we have I plus 1 to n. Okay, so the initially we have m comma n, so that is from 1 to n we have the integers. The location starts from 1 to 9, and when this is given to the partition function, it is dividing that into two sets, okay. So now again you will be calling the quicksort function for this set of elements starting from m to I minus 1 and from I plus 1 to n. So for example, if in this particular case, if the division is made at say 4, okay, then we have a list of elements from 1 to 3 on one set and then from 5 to 9 on another set. So you will be applying the quicksort function for this and then for the quicksort element for this set of elements. And you have a main function here, so where you call the read array function, which is useful for reading the set of elements from the user. And we are using some sentinels, okay, so for to refer the end of the thing, okay. So a of 0, and because we are going to get the values for a of 1 to a of 9, okay. So to mark the end of this array elements, we have two sentinels used here, a of 0 and a of 10, some value minus 9999, and a of 10 is 9999, okay. And then you are calling the quicksort function. So this is your program for doing the quicksort. So now what happens is your activation starts from the main program, okay. Your the execution of your program starts from the main program. So initially it enters the main function. Okay, enter main of. And once it enters the main function, the next function that it is going to activate is read array function. Okay, so then it enters this read array of function. So this read array function, it is not going to call any other function. It is just going to read the integers from the user. Okay. So once this read array function completes its task, it will come out of this function. Okay. So leave the read array function. So once this read array function is called, what it means is that when this function is activated or this procedure is activated, it will create an activation record for this. Okay, and so what does it means? Whatever the local variables that it is having in this function. For example, here we have a local variable I. So this will be pushed into the stack, and once the elements are read and it is stored into the stack, when this function is completed, it will pop all that local variables from the stack and it will come out. Okay, so leave in read array of. Then after that, if you see here, so these are all some assignments only, so it will do that. Then it reads the function, or it calls the function quicksort. So you can see here, enter quicksort of. Actually, it would be quicksort of int m comma n. Okay, so it is passing on the value, the values from 1 to the first element will be 1, and second last element will be the ninth element. So it is calling the function quicksort of 1 comma 9. So after calling that, you can see that it will check for the condition whether n is greater than m. That means the last element should be greater than, not the last element, the position. The position of the last element should be greater than the position of the first one. So then it will call the partition function. So you can see here, now while this function quicksort is activated, and it is executing, and while in that time it is calling another function partition. Okay, so now for partition function also it will create an activation record. And this partition function, it will so this is the example we can take. Okay, this partition function, you assume that it creates a partition at the location 4. So it has now two partitions of elements from 1 to 3 and then from 5 to 9. Okay, so after this partition function, you can see it is calling the quicksort function. Okay, so then again, so now quicksort function is the arguments, if you see, it is from m to I minus 1. So that means from from 1 to 3. Okay, so assuming the I value as 4. Okay, from assume that in partition function it returns the that separator value as 4. So it means that you have here, so you are passing on now only this values from 1 to 3 in the first quicksort function, and in the next quicksort function from I plus 1 to n, that is from 5 to 9. Okay, so you can see here, I enter quicksort of 1 to 3, and in between here, what happens when you call this again quicksort function, again this will go into partition function. Okay, so again this will enter the partition function. Okay, and so again this will be partitioned into 2. So then this will leave the partition function, again inside it will call the quicksort. Okay, so that is why here there is a ditto. So again there is a process going on inside for this quicksort function. So once this is over, it will leave that quicksort function and comes into the next quicksort of I plus 1 to n, that is from 5 to 9. So again the same procedure happening here, and finally when this comes out, and it is coming out of the main quicksort function, and it is also leaving the main function. Okay, so all these activation of procedures during the running time of an entire program, we can represent it using a tree which is called as the activation tree. Okay, so here M represents the main function, R represents the read array function, and Q represents the quicksort function, and P represents the partition function. So now if you see here, now main function, first it calls the read array function, and uh, then it is over and it comes back and reads the activates the quicksort function. And the quicksort function again, it is having partition function, again quicksort of 1 to 3 and quicksort of 5 to 9. Again in quicksort of 1 to 3, what happens, again partition, again quicksort of, so assume that it is having the um, partition as 1. Okay, the I value as 1. So it means that the first set, it will be having only one element, and in the second thing, it will be having from 2 to 3. Okay, so it, since it is having only one element, it means that it is already sorted. And from 2 to 3, again it calls partition, then quicksort, and quicksort of 3 comma 3. So similarly, okay, from 5 to 9, again it calls partition, quicksort. So now all these procedures which are activated one after the other, this we are representing it in the tree. Okay, one after the other. So we can read it out here. So why we are using an activation tree to show the way control enters and leaves the activations. So now we have seen in the previous thing, we are entering the main function, and then we are entering the partition function, sorry, read array function, and then we are leaving that. So the order in which, or the way in which we are moving into the activation and coming out, okay, all these are all represented using the activation tree. And in an activation tree, you can see each node represents an activation of a procedure. Okay, so every node we can see that. So M is a node which represents the main function, and from here we read the function read array. So this is a node, okay, and it represents the activation of the procedure read array, and then you call the quicksort. Okay, so each node, it is considered as an activation, and the root represents the activation of the main program. And if the node A is a parent of the node B, if and only if the control flows from A to B. So here the control flows from M to R. So that means M is the parent of R. Okay, and the node A is left to the node B if and only if the lifetime of A occurs before the lifetime of B. So you can see here this node R is left to the node Q. That means the activation starts earlier before this quicksort activation starts. Okay, so and the children. So for the main function, we have the children, the read array, quicksort, and for quicksort again we have partition, and then again quicksort. Here also again another quicksort from 5 to 9, 1 to 3, so on. Okay, so so one child must finish before the activation to its right can begin. So the partition should finish first, then it should start with the quicksort of 1 comma 3, Once it gets finished, it moves to the next child. Okay, so all these siblings will be going from left to right order, and the children correspond to the activation of the at a node for an activation of procedure P, the children correspond to the activation of the procedures called by this activation of P. So for this particular node Q, we have the children P and this Q and this Q. Okay, so these are the children. And what are these children actually? They are the procedures called by this particular function. Okay, by this parent function. So this is how we can have the activation tree um, by the various functions that are activated during the running time of the program. Okay. So here, these procedure activations should be nested in time. So that means when a procedure calls another procedure, the so if a procedure P calls Q, then the activation of this procedure must come to the end before the activation of P comes to end. Okay. So in the previous program, we can see that M is the main program. So we have called read array, and then we have called quicksort, partition, quicksort, and so on. Okay. So now in this thing, partition is called by this function q. Okay, so partition must first come to an end before this function comes to an end, and it should be in that order from left to right also. So if the activation of q can terminate normally, okay, so the partition function is called and it does the partition, and then it can come out normally. Then what happens, the control will resume directly to the point where it leaves. Okay, in your quicksort function, you have the partition of function, and then you have the quicksort function. Okay, so now the partition function is over. Once it is over, it returns to this function, and where it has to resume after that. Okay, so control resumes just after the point of P at which the call to Q was made. And sometimes what happens, so this procedure, okay, we have called a procedure P, and this may get aborted directly or indirectly due to some error or something. Okay, so in that case, when it is aborted, this cannot continue to execute. So when this is aborted, naturally, automatically, the function that has called this will also come to an end. Okay, so P also will, so here it is P and Q, it is mentioned. So when Q comes to an end or aborted due to some issue, then automatically P also has to be ended. And sometimes sometimes this queue might have terminated because it is not able to handle some of the exceptions. Okay, but in that case, we there is a difference between aborting from the program and then terminating because of an exception. If it is getting aborted, then the function that is calling that should also get that also has to be terminated. But whereas if this particular function is terminated because of some exception which it could not handle, then what could be the possibilities that this P can try to handle the exception. So if P is able to handle that exception, then this activation of P will be continuing. Okay, and but if P is also not able to, if it is also cannot handle the exception, then the activation of P also terminates. Okay, so when Q is aborted, then automatically P will also be terminated. Whereas P, when it is terminated because of some exception or something, then the function that has called that will check whether that can handle the exception. If it is able to do that, then automatically this can continue its execution. If not, then execution will also be stopped. Okay. So this is the format of a general activation record. We have the actual parameters, returned values, control link, access link, saved machine status, local data, and temporaries. Okay, you just study this activation record. What an activation? So we have now talked about that when a function is called, an activation record will be created. Okay, so what an activation record is, what is the content of a activation record? So the activation record will have this actual parameters, returned values, control link. We'll see one by one. So here we can see that what each of these elements in activation record represents. First one is actual parameters. So this is used by the calling procedure to supply parameters to the called procedure. Okay, so what is the calling procedure here? The procedure which calls another procedure. Okay, so if the main function is calling another function, then that function, it provides some of the parameters required for this calling procedure. So that we have seen that for the quicksort procedure, it is passing on the parameters like 1 and 9. Okay, so the actual parameters will be given here. And then the second thing is return value. So the returned value of the called procedure is returned in this field to the calling procedure. So for example, if the partition function is called, okay, so the partition function, initially we have seen that it partitions the value as the value of I as 4. So that value will be returned to the called procedure. Okay, and then we have the control link. So the control link points to the activation record of the caller. So caller is now, for example, if it is the main function may be calling another function. So main function is the caller. So caller has an activation record. So the control link points to the activation record of the caller. Okay. So this would be the caller now, and so this has an activation record, and the control link, it will this points to the activation record of the caller. And access link, it is used to refer to the non-local data held in other activation records. Okay, so all the non-local variables that are present in the other activation records will be pointed to by this access link. And saved machine status, this will be holding the information about the state of the machine just before the procedure is called. So we know very well that once this procedure queue is calling the partition function, so now it should know once this partition function is over where it has to return. Okay, where the control has to return. So the state of the machine, the register contents, the return address, all these information will be stored in the saved machine status. And the local data, the local data holds data that local to an execution of a procedure. So inside this particular local procedure, you may be having some local variables, so that data will be available here. And if any temporary variables are used, then that can be stored here. Okay, so this is the content of the activation record. So this, I'll finish with this. So this shows the downward growing stack of activation records. So you can see first the main function is called, and from the main function the read array function is called. Okay, so first main function is activated, and then the read function is activated along with an local variable I. Okay, integer I. So once this function is completed its task, that will be popped off from the stack. Okay, so the activation for this will be completed, and the integer I that is stored in your stack would be popped off, and this will be removed now. Now it is, so that is why it is shown in dotted lines. Okay, so it is completed now, and that will be popped off from the stack, and then we call the function q. Okay, and where we have again the local variables m and n, and the caller would be passing on this integer value I to this thing. Okay, and similarly, if you see here, then after calling this q function quicksort, it is calling the partition function, and partition function, it will be over after separating the array elements. Okay, so when it is getting deactivating, now it is shown as the dotted lines. Then from there, it is again calling q of 1 comma 3, then that will call p of 1 comma 3, and so on. Okay, so this is just a representation of how these activation records are getting stored in your stack. Do you understand this?
Yes, ma'am.
Yes. So wait and give your attendance. Ruby Kiran,
Present, ma'am.
Vigneshwar,
Present, ma'am.
Alvin,
Ma'am.
Kachapali Verghese,
Present, ma'am.
Alvin Jesuraj,
Present, ma'am.
Gracious,
Present, ma'am.
Prince Walson,
Present, ma'am.
Neil Johnson, Neil,
Ma'am is present, ma'am. His mic is not working.
Joshua Felix,
Present, ma'am.
Dinesh Kumar,
Present, ma'am.
Pratyu Vishwak,
Present, ma'am.
Jocelyn,
Present, ma'am.
Prince,
Present, ma'am.
Jenish,
OD, ma'am.
OD. Chandrakant,
Present, ma'am.
Saradi,
Present, ma'am.
Abraham,
Present, ma'am.
Jonathan,
Present, ma'am.
Frederick,
OD, ma'am.
Manoj Kumar,
Present, ma'am.
Muthu Aravind,
Present, ma'am.
Anish,
Present, ma'am.
Paul Nitesh,
Present, ma'am.
Srivarshan,
Present, ma'am.
Isaac Emmanuel, Varun,
Physical admins, ma'am.
physical attendance, Pavitrapadi,
Present, ma'am.
Febi Sara, Febi, Ashwin,
Physical, ma'am.
physical, Agnes,
Present, ma'am.
David,
Ma'am is also present, ma'am.
okay, Randlin,
Present, ma'am.
Krubakaran,
Present, ma'am.
Evangelina,
Hello.
Ajay Martin,
Present, ma'am.
Sujit,
Present, ma'am.
Nitish, Nitisha,
Present, ma'am.
Anmol, Anmol, Sumit Kumar, Daniel John Paul,
Present, ma'am.
Danush,
Present, ma'am.
Bhaskar,
Present, ma'am.
William, Terence,
William chat box.
Terence. Okay, thank you, students. You may leave.
Thank you, ma'am.
Yeah, thank you, ma'am.
Thank you, ma'am.
Yeah, thank you, ma'am.